Hello everyone, so this is the second video on the bubble temperature and pressure and dew temperature and pressure. So in the first video we derived expressions to find bubble pressure and temperature and dew pressure and temperature. And now in this video we're gonna try to sketch the phase diagram for bubble pressure, temperature and dew pressure and temperature. So in our question, we had a mixture of 30 mole percent of benzene and 70 mole percent of toluene. So as always, we start by importing our CHE tools and all the libraries that we need. We're going to be using NumPy, SciPy Optimize, like root solver from SciPy Optimize, and we're going to be using Plotly for plotting purposes. And as we always use the dark Plotly, we're just using the Plotly dark. Okay, as we are working with the mixture, benzene and toluene, we need to work with the CHE tools in order to have their properties. So let's just have an array class with their properties. Let's have properties with CHE dot props. Yep. So it's going to be props of what? So we have benzene and we have toluene. Yep. And let's just run it. Yes. Now we have a class with all the properties for benzene and toluene in an array form. Okay. So now let's have the let's have an array for their mole fractions. So let's have x is equal to numpy array, so it's 0.3 to 0.7, and let's have two separate arrays for bubble and dew temperature and pressures. So we have y, it's going to be exactly the same, b dot array 0.3 0.7. Now let's just run it. We forgot the brackets. Yes, here we have typo, we forgot the brackets. Oops. Yes. And now it should work. Let's just run it. Yes. Okay, and now as we have four equations here, we can try to have four separate functions to calculate all the variables. So let's have our first function, which is for bubble pressure, and it's going to take a variable, so it's going to take the x, which is the so x and y. So x is the x is the amounts of compounds in liquid phase, and oh no, sorry, x is all the amount of compounds in the vapor phase, and y is all the amount of compounds in the liquid phase. So for the bubble pressure, we need to have it in the vapor phase, so we're going to use x. So, and it's going to take the value of temperature, because we're going to be given the temperature and we'll be asked to find the bubble pressure. Okay, and what's the next step? Okay, for the next step we need to return the equation we have. So it's going to be this numpy sum, yes, because it's in a form of sum. Yeah, and it's going to be the x times the saturation pressures. So we can get that from CHE tools. So it's going to be p dot props, pvap at a specific temperature. Let's just run it. Now we have our first function to calculate the bubble pressure. And for the second, and now let's have the second function for our bubble temperature. And it should take the mole fraction of compounds in liquid phase and the pressure. And it's going to calculate the bubble temperature. So, but for this equation, we know we are trying to find T, right? It's not an equation like T equals something. So what we need to use is we can find the temperature that makes this thing, like the right hand side, equal to the pressure. So for that, we can use the root solver so that it finds the temperature which makes their subtraction equal to 0. So first we can have another function inside the nested function with the equation that is going to take the vector, and the vector is going to be our temperature, like and it's going to be the first thing from inside of a vector, and it should return the equation for the right hand side, which is going to be this thing minus pressure. Okay, so this thing itself is the bubble pressure, right? So it's going to be bubble pressure at specific x and t. So it's going to solve for t minus pressure that we are given. And it's the nested function, and the main function has to return the root solver, has to do the root solver for the function equation. And let's give the initial guess for the temperature. Let's have it as like 298 kelvins at the room temperature. And it should isolate the X array and get the first item from the X array. So this is the bubble temperature. So now let's move on to the dew temperature. So for dew temperature, we're going to define another function with dew temperature. And again, it's gonna take the X and the, let's just start with the pressure. It's gonna take the X and the temperature. Oops. dP. So it's gonna take X and the temperature. Depreciation warning. I don't know what does that mean, but oh yeah, for the dew pressure we should use the amount of mole fraction of compounds in liquid phase, so it's going to be Y. Yep. And then so it should return, it's going to return this equation. Yep. Oh no, this is the dew pressure. Yeah, this is going to return this equation. This was the bubble temperature. So it's going to return this equation here. So it's going to be 1 over sum. So we're going to use numpy sum of Y over saturation pressure. So it's going to be P vap at a given temperature. So let's just run it. And for the dew temperature, we're going to do exactly the same thing as we did for bubble temperature. So we're going to have nested loop. So we're going to define equation so that we can use it to use the root solver. Okay, so it's going to be the equation for the right hand side. So it's going to be returning. Oh, let's just first isolate the vector. So it's going to be vector is going to be the temperature, the first item in the array. Yeah. Oops. So it's going to be returning the subtraction of that. So it's going to be dew pressure, right? So it's going to be returning dew it's going to calculate due pressure at Y, it should find specific pressure so that a specific, oops, it was G, yeah. So it should find specific temperature which makes this go to 0. It is pressure, right? And then it was a nested loop. For the return function, we're going to use the root solver with the function equation provided with the initial guess. It's going to be 298, like the standard room temperature. And we're going to isolate the X array, the first item from the array. Yeah, now we have 4 equations to calculate four functions to calculate bubble temperature, bubble pressure, due temperature, and due pressure. Yeah, and now let's try to start plotting it as we are trying to create the phase diagram for these, right? Okay, so let's for the x-axis on our plot, let's have the saturation, the mole fractions of a more volatile compound. So we're gonna tell that x. So we're gonna see the relationship between the temperature and pressure, as the mole fraction of more volatile compound increases. Okay, so we're going to create an linearly spaced variables numbers. So it's going to be lin space. Let's start with 0, go 1 to 1 with let's have 11. And for this is a mole fraction of a more volatile compound. Then the mole fraction of less volatile compound should be 1 minus x1. Yeah. And then in the question here, we are provided with the initial temperature, and I think I did something wrong here. So it should have been 393 393.15 Kelvin. Okay, let's just have it in our equation. We don't need this. Okay, so our temperature, that is for finding the bubble and due pressures. So it's 393.15. Yeah. And what is our P saturation? So our P saturated pressure is, let's have it as P sat is equal to P vap, like vaporization pressure at a given temperature, right? And let's create the list for all the pressures that we need, all the bubble pressures. So list of bubble pressure. Okay, what do we need inside of our list? Okay, so we need xi, which is the mole fraction of a more volatile compound, multiplied by the saturation pressure starting from 0, plus let's have a bracket here so that it's not confusing. Yeah, so then it's gonna be, I think I have too many brackets. Yeah, I think then it's the mole fraction of the second compound, less volatile compound, multiplied by the P saturation for the second element, which is the toluene, right? The benzene is the less volatile. Okay, let's create another list for due pressure. We can create an empty list for this one. And in order to find the dew pressures, we're going to use our function inside of a loop. So we're going to create loop for y2. It's going to be the mole fraction of compounds for dew, like in liquid state. It's going to be in y, and it should be exactly the same number as x1. And oh, I'm forgetting the column. And then again, our y2 is going to be equal to 1 minus y1, as the mole fraction, it always have to, like the sum has always have to be equal to 1. And then let's have an array of y. MP array. So it's going to be, so y is the mole fraction of compounds in liquid state, and it's going to take y1 and y2. And for our list of dew pressures, we're going to use list append. Oh no, I'm using correct append. So what we're going to append? So we're going to append the function to find the dew pressure at y at a given temperature. Okay, so this is going to be the two lists for our bubble pressure and dew pressure. Let's just try to plot it. Oh, we have an error somewhere. So it says function object is not subscriptable. Yeah, I see here. I should have used the brackets instead of the square brackets. Again, it says function, built-in function or method object is not subscriptable. Let's see where our error is. And again, I forgot the brackets. And now it should be good. Okay, let's just try to plot it. Okay, let's create a figure. And I need subplots. Subplots with one row and two columns. Columns 2. And we're going to use, as always, scatter plot, fig add scatter. And for the x-axis, we're going to use x1. It's going to be the same for everything, as like y1 is also equal to x1. Okay, so and for y-axis, we're going to use the list of bubble pressure. And it's going to be in row 1, column 1, and let's have the name as bubble pressure. And let's just copy it and have another scatter plot for our dew pressure. So it's going to be again in the same column, same row, but we're going to use another list. So we're going to use dew pressure. And we have to rename it. It's going to be dew, and let's just run it. Oh, here we have an error, make subplots. So here we have an error, subplots. I think I forgot S here. Yes, and now here is our graph. So the purple one represents the bubble pressure. Yes, it is logical that it should increase linearly as the mole fraction of less volatile compound increases. And this is the dew pressure, which also makes sense because it also has to increase. The bubble pressure has to increase. Yeah. Okay, here there's a space, there's a second column. So for this part, we're gonna have another phase diagram for our bubble temperature and bubble and dew temperature. Okay, let's create another list. Before that, we are given the pressure of one atmospheric pressure. So let's just it's gonna be yep e to the 3, yeah. And then let's create a list, two empty lists for bubble temperature and dew temperature. And let's use our functions to fill this list. So we're going to use again the loop, and now this time I'm going to mark it as Z1 so that it's not going to be a mess. In X1, yeah, and then our Z2 is going to be equal to 1 minus Z1, and let's create array Z equals numpy array. So because we're gonna need the sum of these like Z1 and Z2, so this is so that we can use it inside of our function. So we're gonna use list bt append. So it's gonna be bubble temperature function. It gets Z1, it gets Z, and pressure, the provided pressure. And our list dew temperature dot append gets the dew temperature equation for Z and the provided pressure. Let's just run it. Invalid syntax, we have Z in X1, Z1 and X1. I'm not sure. Oh, here I forgot the columns, and then in this array, again the same mistake. I'm using the square brackets instead of just regular brackets. Okay, let's just run it again. This is append. What is the error here? Name list. All the typos. I fixed the typos. Again, list is not defined. List dt. I hate typos. It's list here and with capital T. Again, v is not defined. V is not defined. Oh yeah, I forgot. So here it says our vector for, yeah, I used two different variables, variable names, which resulted the confusion. Okay, let's just copy these two. So we're gonna plot the second column, and it's gonna be the bubble temperature and dew temperature. Yes, and they're gonna be in the column 2. And yeah, it's gonna be bubble temperature and dew temperature. And let's just run it. Oh, I think I made a mistake somewhere. I found a mistake here. We used y instead of x. Yeah, and if we run it, yeah, now this is correct. phase diagram for our bubble and dew temperatures. Yes, and as we see, as the fraction, as the amount of more volatile compound increases, more fraction of more volatile compound increases, the temperature should decrease. So in this video, we'll look through the bubble pressure and temperature and dew pressure and temperature. We derive the expressions, and we write the Python code to create the phase diagram for our bubble and dew temperature and bubble and dew pressures. Thanks for your attention.